Richard Steenbergen from nLayer Communications, and we're going to be talking about something that's very similar to what was just spoken about, unfortunately, although we kind of have a little bit more operational bent on it. We give you the information that you need to be able to go out into the real world and do this in your network today, hopefully with data you already collect. So we're just going to be talking about using NetFlow data in combination with routing information to further the ideas of peering networks and even people who buy transit. So the first question is, why would you even want to do this? And there's a lot of reasons. You might be trying to defend yourself against depeering from a large provider. You may be trying to peer with folks and you need to convince them to peer with you. You may be someone who just buys transit today and really wants to find out where you send your traffic so that you can peer with a few strategic folks and reduce your transit utilization. Or you may just be a person buying transit who wants to look into the transit providers that fit your needs best, that have the best routes to places where you send your traffic. So all these are pretty common. There's not really anything new there. And the way that we look at our data and the way that we look at the flows that occur in our network is NetFlow. Hopefully everyone's heard of NetFlow in some respect. Basically it takes data, takes packets that are observed on a network, aggregates them via the 5-tuple, that is the source IP address, destination IP, IP protocol, and if it exists, source and destination port. Takes that information and builds a big table out of it. Packets that come in that match somewhere in that table have their bytes, etc., counted to that table row. And if they don't match, a new entry is put into that table. If a packet that ends a flow, for instance, something that ends a TCP session exists, then that session is immediately sent to the NetFlow collection system. If not, then it's exported at some interval that an administrator can define. So NetFlow only gives you the raw data. It doesn't give you anything else. You have to take your NetFlow data and really figure out what's going on inside of your network from there. Some NetFlow implementations give you origin AS or peer AS information, but really a peering network or a network that wants to understand their traffic flows needs a whole lot more information. And especially to construct a very good peering strategy, you have to have more information. You have to have information about where you send traffic to through your transits so that you can peer with those folks and things of that nature. And for peering networks especially, it's important to remember that the real question is, where can I send my traffic, not where do I send my traffic today. So we take all the NetFlow information and we basically just throw out everything except the destination IP address and the number of bytes in the flow. This works really well with sampling techniques because we're just doing a statistical analysis to figure out where our traffic goes. We don't have to worry about aliasing. We don't have to worry about absolute metrics. We're just trying to get a statistical average of where the traffic flows inside of our network and to other networks. So we throw out all that information, and then we have to collect RIBs, routing information bases. The basic idea is that we're going to take the routes that a peer would advertise to us and figure out how much of our traffic we would send over those peer routes if they were preferred inside of our autonomous system, etc. So basically all we have to do after we've done that is change what AS we account the traffic to in the AS path. We'll get into the details here. But first a word about multi-homing, about why the entire technique works. Basically there's a ton of multi-homing. Very, very few people are singly connected to any one ISP. What that means is that there are lots of different paths and that BGP obscures those paths since it only propagates best path information. Once the best path has been propagated, all of the other feasible paths are no longer visible to anyone outside of the provider that discarded them. So what that means is that we have to look at routing data. We have to collect our routing data from sources outside of our own network in order to be able to project our existing traffic onto these onto the peers that we want to have access to. So the first thing we do is we collect our peers, or the routes for the person we're trying to project traffic onto out of band somehow. This could be done with a looking glass. This could be done by asking the peer, hey, what routes would you send me if we were peering? This could be done through, we have a number of different links at the end which give some examples of where you could go to find this sort of information. And then you also have to include the AS path on the right side there. This same technique applies for transit providers. That's especially where that's useful. For now, what we're going to talk about is setting n equals to 1. N for us is simply what AS in the AS path we count the traffic to. So if we set n equal to 1, we're accounting the traffic to the first AS in the AS path. We then take all of our traffic, take all of our NetFlow traffic, and we push it through this new rib. We say, okay, the destination address of this NetFlow flow is 111.2.1.1, so I'm going to account it to the first record in that rib up there. And because n equals 1, I'm going to account it to the first AS there. So what we end up with at the end is a list of how much traffic we would send to each autonomous system that we have in our rib. You can even expand this analysis quite a bit to figure out where you send the traffic to today. So if you send the traffic to your transits, you're a little bit more likely to want to move it off onto a peering session. If you send it to existing peering sessions, perhaps it's not quite so important. We've got graphs later in the presentation that show this in a little more detail, but that's a really important analysis point when moving forward. And now Richard will do the rest.
So now we start talking about applications as far as actually being used in peering, not just general data analysis. So obviously some networks are going to be open peering, whether it makes financial sense for them or not. They have a policy, they're open peering. We call them peer leaders. That term came from Ren. And some people are going to be closed peering. They just have a natural inclination towards that for whatever reason. Some people will take a little bit of convincing, and some people will just never peer with you at all for whatever reason. So some of the reasons that happens, why they don't want to peer with you, just because you're a billion-dollar network doesn't mean you have any idea of where your traffic goes. I've talked to lots of people that claim to do traffic analysis, and when you actually drill down into it, they don't do much at all. A lot of people rely heavily on trial sessions and just general speculation. Another reason is that being on the inbound side, it's much harder to figure out where that traffic is actually coming from. On the inbound side, you just don't have access to enough data to make some of those decisions. So the person with the outbound view may actually be in a better position to make the determination, no matter how well-intentioned the inbound person. And then, of course, who needs actual information when you have company Kool-Aid? By that I mean, if a network considers themselves to be a superior network in a certain region, if they think, well, we have 16 million eyeballs that you can't get to any other way but us, why do we need to peer with you? You don't even need to look at the data to assume that. So having proof is a good way to, when you are interested in getting peering from some of these folks, to separate yourselves out from some of the people who are running global, fully redundant OC192 backbones that are actually zero committed MPLS on someone's Zebra router. There's a lot of that going on these days. So having detailed information really helps stand a network out when they're going for peering. This didn't quite come out as well as we'd hope. So there's the technique called donut peering, which is when someone won't work with you, work around them. Because multi-homing is so pervasive in the core of the internet, even if you aren't multi-homed, your upstream probably is, unless you're buying from a tier 1. So really most of the routes, even a tier 1, 90% of their routes are multi-homed through someone else. So if they won't work with you, you go through them, you go around them. So the ways that you go around them, as always, you can try to peer with your customers directly. You can try to sell their customers, or you can try to find their customers who may be more obliging to working with you. So really the question is, how do you find that data? And that's where this tool comes in. So to start, for example, you obtain a rib for the peer in question through whatever means. Then if you set n equals 1, you're looking at the first hop in the AS path. Obviously, you're getting an accounting of how much traffic you send to that network. And I'll just give you an example. A network the other day approached me and mentioned that they had 40,000 customer routes, and I went and checked my rib, and I was getting 3,500 from my transit provider, so around 10%, less than 10%, and I was actually using around 900, so a really small amount. There's a lot of multi-homing out there. So then if you look at n equals 2, you're looking at where your traffic goes to their customers, and that's all your traffic, including what you're currently sending to transit now and what you're currently peering out now. So another application for this is picking transit providers. Just because you're not a peering network doesn't mean you aren't interested. If you're concerned about where you're sending your traffic, or you have a high volume of traffic, you're interested in how your transit provider is handling that, and also trying out new transit providers virtually. So what you can do is obtain a route map for a transit provider, either your own or someone else, and project your data onto that. See what would happen if you were to send your traffic to that network. And based on their peering policies, who they interconnect with, and how they preference routes, it can be vastly different. And then you can concern yourself with their capacity to certain networks, or their peering policies to certain networks, based on how it actually influences your traffic. And that lets you pick providers who are going to support your peering strategy. So, for example, you may want to buy transit from someone who doesn't already peer with a target network that you're trying to reach, and then you can actually show the target network that you're trying to peer with how much of that traffic is being diverted around them, and potentially interest them. So now we get to the pretty pictures. This is an example of how possible it is to donut around certain people. The traffic in green here, this is from a medium-sized content-heavy network in the U.S. And the traffic in green is traffic that's already being peered out that's going to any of Sprint's routes. It's in the over 10 gig range. And the little blue line at the bottom there is how much actually has to go to transit. So you're really looking at around a 15-to-1 ratio against the big core networks if you really want to get aggressive in donut peering. So here is a more practical example of a medium-sized network, medium-large-sized network, that is well known for restrictive peering policies and depeering activities. And before anyone accuses me of being mean, that's the description I was told to use. So here, for example, you see 4 gigabits per second peak traffic going to them, and you see that 3 gigs of that is already peered out through other peers. And you see that 1 gig is being sent to transit. And so that network comes along and says, well, great, we're 25% of the transit traffic, we must be big and important. But then we look at a more detailed analysis of where we send those 4 gigs. So this is just taking the raw output of our system and sticking it into a pie chart, basically. You see the different individual networks that you're able to peer around: AboveNet, Cogent. Can't really read it from here. The usual folks that share a lot of their multi-homed customer base. And then you see how much is sent to traffic, around 27%, which is a little over a gig. Then you're interested in what your transit provider does with that gig that you send them, because your transit provider also has its own customer base, has its own peer base that you don't have, and has its own policies. So again, you see in red that only 17% of that traffic, or 180 something megs, is actually sent out of that 1 gig to that network. The rest goes to UUNet, Sprint, Deutsche Telekom, Open Transit, other customers, the usual suspect folks. So at the end of the day, the conclusion that you come to is that a network that thinks that they have a large number of eyeballs who can't be worked around, where you need to come to them to pay settlement to peer with them, in reality is only seeing 4.8% of the traffic, or out of the potential 4 gigs that they could be billing their customers for, they're only seeing 187 megs. Now, another argument that they often put up is, well, that's all going to flat rate customers, that's going to DSL customers, we're not going to see an increase in billable traffic if you send us additional traffic. And that's where the next step in the tool comes from, being able to identify exactly which of their customers. But clearly here you see that only 187 megs are single-homed. The actual amount of single home is probably less than that, but just getting the traffic down to 187 megs is already making it pretty inconsequential. So the rest of that traffic, where it goes, obviously it bypasses them, either being peered directly with their multi-home customers, or even worse for the target network in question, goes to their competitors who are billing for that traffic. So by looking at the next AS hop, the data that we can gather from that is we can either convince them, we can say, listen, here are the 20 networks, the top 20 networks, here's the exact amount of traffic that we'd be sending to. You can easily look at how much you charge them for transit and do some multiplication and figure out how much additional revenue you'd be billing. Or if they're still not convinced, now you have a list of customers to go either peer with directly or start poaching. So there's a bunch of flaws in the system. So far we've only talked about outbound traffic. That's because outbound traffic is the only thing that's actually easy. Inbound traffic is very hard. You really have no idea from looking at external routing information where traffic could come from. You have so many cases where a network is sending you traffic but isn't the preferred path for the reverse, or is the preferred path for the reverse but isn't sending you traffic. Also, you need to gather these ribs. It's hard work, and you have to maintain them. There's no existing unified system for gathering peer data. If I want to pick a random network like SBC and I want to say what of their routes I could send traffic to, there's no easy source that I can go to get it, certainly not in real time, and they may or may not give that information to me based on their policies. And obviously, you're not going to accept every prefix from every potential peer. So while this gives you a little bit more accurate data, say for example, you're considering turning up a new peer with 40,000 customer routes, and you're only seeing 3,000 of them today, you're obviously not going to install all 40,000, but you're obviously not going to install only 3,000 either. So now, we actually have a tool that does this. Unfortunately, we were not able to get the SourceForge registration done in time. So if you go to this link right now, it will give you nothing. Wait a day, it will be fixed, I promise. We did this in 2 versions. One is a simple Perl version. I wrote a version in C, spent several hours writing a nice little mtry-fib and making it optimal. And then Nathan came along and wrote the Perl version in 15 minutes and about 60 lines. It consumes a little bit more RAM, but it's obviously a lot more flexible, so there's a lot of area to work with what you're most comfortable with. The Perl version is intended to work with captured data from flow tools. So if you record a 5-minute snapshot automatically, which many people are already doing, you just throw this at it. It takes 10 seconds to run. There's a high startup overhead, obviously. But you load the rib, you parse the data in your 5-minute sample, and you get some simple text output. The C version is intended to be more long-running. You are able to run it as a daemon, have it run over long term, or have it process many ribs. I'll give you an example of just the data analysis that we do. We maintain somewhere over 200 ribs for all of the peers that we're interested in. We take in a lot of data from a lot of routers, so certainly by the time you get to that point and you want real-time output and you want to direct this information into RRD tool or something to that effect, it helps to have a longer-term version. So there's some other resources here for getting the views that you need. PCH runs a looking glass that has dumps of all the people that peer with them at major exchange points around the world. Some of the more closed peering people are not open to giving that data, so tough luck. But some people are. You know where to get it. Renesys is also working on a collection platform for doing this kind of data in the future, perhaps to provide an automated system where you can just say, give me the routes for this AS, and they have it based on kind of a route views type project, but dedicated solely to obtaining customer and peer routes for this data. And of course, if push comes to shove, you can go out there and start looking at random people's looking glasses. Hurricane Electric is a good example of a very open peering network with a reasonable reach that has a public looking glass. So there's a lot of small data that you can mine there. That's about it. Questions?
I had some interesting observations. One of them is that going to some large US carriers with this kind of approach, we actually had a response that talking about ways that they could generate additional revenue to their multi-homed customers by something that looked like traffic engineering could get them in trouble because the Sarbanes-Oxley auditors told them that they weren't allowed to do that because that might be unethical. So that's one thing to be aware of. Now, whether that was pure bullshit that someone made up on the fly and said with a straight face and we bought or not, I don't know. Another thing is when you look at ways to get into a network, you have the donut, you have their transit providers, their peers, and their customers, or peering with them. Another thing that you can sometimes do is buy from their customers, especially if their customers are asymmetric. That may be easier for a content delivery type thing to do than if you actually have to put lines in, but you can often figure out who their largest customers are and not only look at selling to them, but if they are asymmetric in the directions complementary to you, partner up on their quote-unquote transit connections and do that.
That's certainly a good idea, and that works really well for CDNs. Obviously, I come at this from the angle of a network. So
asymmetric transit networks or eyeball networks or hosting networks, it works for it.
It's a very good idea. And if multi-homing is unethical, then we're all screwed. Any other questions?